So in last class, we have seen the fundamentals of supercharging, turbocharging. We also seen the fixed geometry, wastegate, turbocharger, variable geometry, turbocharger. So today we will be seeing the turbocharger matching and then the compressor and turbine efficiency. So we have seen volumetric efficiency, what is the airflow requirement last week. We also seen the supercharging, turbocharging principle, why we need to have the supercharger, turbocharger, and different types of supercharger we have seen, and what is the disadvantage of supercharger, and what are the key components of turbocharger we have seen. We also seen the layout of the turbocharger. We have seen the limitations of turbocharger where you have some turbo lag, and how that aspect ratio will be overcome with the help of the variable geometry turbocharger. And we have seen the need, why we need to have GT or shortly called as variable geometry turbocharger. We have compared the variable geometry turbocharger with the conventional turbocharger. So now we will see the turbocharger matching and then the compressor and turbine efficiency. So we'll see the compressor mapping. So the x-axis is nothing but the mass airflow rate, okay, and y-axis is nothing but the pressure ratio. The pressure ratio is basically the outlet pressure to that of the ratio between the outlet pressure to that of the inlet pressure. The inlet pressure, the mass flow rate of the air which is entering into the cylinder, and the exhaust pressure is basically the exhaust gas flow which is coming out from the exhaust system. So that ratio you call that as a pressure ratio. And you see here, I told you the turbine RPM will be close to 1 lakh to 1,50,000 RPM, depending upon the speed and then the airflow rate and then the mass flow rate of the gas as well. You see here, this indicates the RPM of the turbine, and this the percentage. Okay, the percentage indicates the percentage of the efficiency of the compressor. Okay, and again you have a limit called surge limit. This is the operating threshold limit for say for example, if the flow rate, if the mass flow rate of the air is said to be 1.5, and if the pressure ratio is 2, then you need to select the value. It will come somewhere here, and you need to select the value considering about the surge limit. Okay, I told the surge limit is the operating zone where you need to select between the surge limit and then this is the check final limit. Okay, so in between the surge limit and the check limit, you need to select the efficiency of the compressor and also the RPM at which the turbine needs to perform. So you see here, suppose if I selected the 2 as a pressure ratio and 1.5 as a flow rate, then you need to select the value straight away above the surge limit, and you will select something in the efficiency close to 75%. Okay, and accordingly, because you should not give overload to the compressor also. Suppose select efficiency higher than what is required, then again you are giving excess load. Will also, even though the efficiency is going to be higher, but you are unnecessarily increasing the pressure, or you are unnecessarily increasing the flow rate which is not required. So it's always essential to select the best required efficiency. Okay, too much efficiency is also not a viable one, as it will affect even though the performance we can meet, as it will affect the durability and then the lifetime of the turbocharger as well. And T1 is nothing but the inlet temperature, and P1 is nothing but the inlet pressure. I told the ratio, pressure ratio is basically the outlet pressure to the inlet pressure, and the air flow rate is the correct air flow rate. The flow rate is nothing but uh, the mass flow rate of the medium. So here the unit is kilogram per second, and n is nothing but the speed, okay, at which the turbine performs. Okay, so and T1 is nothing but the inlet temperature. And according to this, you need to select compressor mapping. And you see, it is very much important. You need the compressor and turbine engine matching, considering the efficiency. So we have seen the graphs showing the air flow rate and then the pressure ratio. So now we need to see how we are going to match the engine turbocharger turbine and also the compressor. So there's a procedure is there, and you need to go with that procedure. And you see here again there is one more graph showing the mass flow rate. So here the mass flow rate is nothing but the gas flow rate. Okay. Uh, uh, so the exhaust gas basically is consists of a thing where the flow rate strikes the turbine blade. And you see here again, you need to look at suppose if you find the pressure ratio 1.8 and the mass flow rate as 1.5, then you need to select the actual efficiency considering uh, the relationship between the compressor and the turbo, and you need to select based on the temperature and also the fuel flow rate and also the mass flow rate. So here there is a big procedure. First, you need to consider the engine inlet conditions. Then, what you need to give is what you need to consider is you need to consider the engine volumetric efficiency. And again, basically the volumetric efficiency deals with the mass flow rate of the air. Okay, higher the mass flow rate, you get the higher volumetric efficiency. You need to determine the volumetric efficiency of the engine. You need to understand your inlet condition, then you need to calculate your volumetric efficiency, then mass flow rate of the air, and again accordingly you need to the speed of the turbine. According to the speed of the turbine, you need to see what is the speed of your compressor, and you need to map okay according to the pressure ratio and the flow rate, and you also need to consider what is the fuel flow from the engine map. And then again, you need to find out the exhaust temperature, engine exhaust temperature. So this is the inlet condition. Again, also look at the exhaust temperature, exhaust pressure. So when you get the temperature, you will also get pressure. So exhaust pressure divided by the inlet pressure, you get the pressure ratio. And again, you need to find out what is the turbine speed, and then based on the turbine speed and also the mass flow rate, you can also get out what is the flow rate in the x-axis. So according to this, you can select the efficiency percentage, and then what you is finally you need to determine the turbine power from the turbine on mapping, and how much power you're going to get. Basically, that this also you can obtain it, and finally you need to do the iterations considering all the input condition, outlet condition, and also the efficiency and also the power. As far as the content of the gas exchange process is concerned, it deals with a lot of basics and also mostly it's basics and some of the flow patterns of the exhaust of the inlet and the exhaust inlet air and then the exhaust gas. So we'll be seeing the inlet and the exhaust process in four-stroke cycle. This had been already covered. Basically, we have seen the four-stroke intake stroke, which is nothing but the suction stroke, and then the compression stroke, and then we have seen the power stroke, and the last one is the exhaust stroke. So considering that, we need to study what is the different process, and what are the different pattern of the each and individual stroke which will complete the cycle. And we have also seen the volumetric efficiency, and we will slightly elaborately see the volumetric efficiency also here. And the flow through walls. Okay, basically the air is coming in the case of the diesel engine. Air and fuel mix comes during the intake stroke in the case of a gasoline engine. So how the flow pattern is happening inside the engine, that also we will be seeing. And then I will just touch upon this subject, but I will not go in depth about the exhaust gas flow rate and temperature variation, but I will just give you an overview. And you'll see the scavenging in two-stroke engine. Scavenging is basically you are removing the exhaust gas from the exhaust system to the atmosphere by forcing the air, by increasing the pressure of the inlet air, and you are expelling the exhaust gas to the exhaust system. Basically, the scavenging. You will see the scavenging and then its types of scavenging. And in the case of a two-stroke engine, you don't have the valves. Okay, you have only ports. Okay, you have inlet port, transfer port, and also the last one is exhaust port. Inlet port will allow the air mixer in the case of a diesel engine, and air fuel mixer in the case of a gasoline engine. And transfer port will transfer the air and then the fuel to get compressed below the piston, and which is part of a combustion chamber. And you have one more part called the exhaust port, which will expel the exhaust gas to the atmosphere. Uh, and the very important topic we will be seeing today is the valve timing diagram for a two-stroke, four-stroke diesel and gasoline engine. So this is very much important. Okay, and even with respect to exam point of view also, it's very important. You need to draw the diagram. Okay, and I will explain that. Give more focus towards this valve timing diagram, and we'll see what is the overlap. Okay, so these are the overview. And apart from that, I am also planning to cover the topic called the fluid motion in combustion chamber. So it's basically so in the fluid motion of the combustion chamber, there are different types of the turbulence type. Basically, we are going to create the turbulence, and you'll be seeing the swirling motion, squeeze motion, tumble motion. You have the different types of the combustion chambers. One is a divider combustion chamber, crevice combustion chamber, and we will see some of the mathematical model and the computer simulation, and some of the simulation results also we will see it. And see, this is very much important. Okay, you have to look at the different types of combustion chamber which is there in an engine. Okay, this is very much important. So give more focus towards this combustion chamber, different types of combustion chamber that you have. Also, you give importance to the valve timing diagram. Okay. Remaining things today I will be a bit fast, but okay. So first we'll see the scavenging, then go to the valve timing, and then the timing diagram basically. Okay. So scavenging is basically, it is applicable for a two-stroke engine basically, irrespective of the type. It can be a gasoline or a diesel. So here this scavenging is basically for a two-stroke engine. What is called scavenging? It is nothing but the process of removing the burnt gases, okay, from the combustion chamber of the engine cylinder. Basically, you are expelling the exhaust gas out. Okay, that is called as scavenging. So you have three types of scavenging. One is cross flow scavenging, backflow or the loop scavenging, and the third one is the uniform flow scavenging. So you see here, you are going to expel the exhaust gas to the exhaust system by forcing the inlet inlet air with some high pressure, okay, with some pressure system, so that the inlet pressure it is coming from the inlet air strikes and it pushes the exhaust thing to the exhaust system. So here the pattern is going to happen in a cross flow. You're going to have the pattern in such a way to cross the inlet. So the blue indicates the inlet pressure and the exhaust is nothing but the exhaust system going to the exhaust to the atmosphere basically. And in the case of the loop scavenge, you can see this is the inlet air pressure, which will ensure that it is going to expel or remove the burnt gases from the combustion chamber with some striking with some pressure. In such a way, it creates a loop in it. Okay, you see, this is the loop. Okay, it forms a loop like this, and it again expels. And in the case of the loop scavenge system, it is bit the flow is bit slightly complicated because unlike in the case of cross flow, you're striking the air which is coming to from the inlet into the combustion chamber. You see that the arrangement can be easy, and but in the case of loop scavenge, you're going to reverse the arrangement such a way. Uh, you're going to divert it and then you are going to have it. But again, it all depends on the designers how they want to have. But they will decide which one is the best suit of the type for them for their application. And in the case of uniform scavenge system, uh, so this is the combustion chamber where whatever the combustion is going to happen about the piston. So the combustion will happen with the help of both air and fuel. Air is coming from the inlet, okay, and the inlet will be operating. The inlet air is coming to the system with the help of intake port, and you have the transfer port which will transfer the inlet air and the air fuel mixture will happen. The combustion will happen aboard the piston, basically in the which is nothing but the combustion chamber. And you have one more port called exhaust port, which will expel exhaust gas to the atmosphere. So here, the uniform scavenging system, um, the flow is going to happen uniformly across this combustion chamber, and you're going to burn. You're going to remove the burn gases from the combustion chamber to the top of the atmosphere. So you have these three types, and these three types is very well explained in John B. Haywood in the chapter 6. You can see that for more explanation. Just I have given you the overview, but you can get more in-depth details about the scavenging. And always ensure that scavenging is going to happen only in the case of a two-stroke engine. Okay, not in the case of a four-stroke. Now we will see the engine valve timing diagram. Okay, I will give more focus towards the engine valve timing diagram today. And this is very much important. Okay. Firstly, we need to read how the engine valve opens and closes. I told the first class I told you, you have the valve system where it will open and it will close such a way it will take the air in and it will expel the exhaust gas out. So we will see the valve timing diagram for both two-stroke and also the four-stroke. So here the engine camshaft opens and closes the valve at a specific interval, and the timing of the opening closing valves is always specified in degrees. So here we have some degrees, okay, and corresponding to that of the position of the engine piston. So engine valve timing is very much important, and it's very critical process in the case of IC engine. And it will also ensure the power and torque of your engine. We will see the valve timing diagram. First, I will complete the four stroke, then I will come back to the two stroke. This is the valve timing diagram for a four stroke petrol engine. So again I'm going to divide the engine, the four stroke petrol engine, gasoline engine, into two type of engine. One is a low speed engine, another one is the high speed engine. Okay. You see here First, I will complete a low speed engine. So this is the TDC, which is nothing but the top dead center. This is the BDC, which is nothing but the bottom dead center. See, you always need to remember one thing: the inlet valve opens where the air enters into the air in the case of diesel, and in the case of the petrol engine, air and fuel mixture. Okay, you see here the inlet valve opens. This is the first process. So first process is the inlet valve opens. Okay. So when the inlet valve opens, the air fuel mixture comes into the combustion chamber. Okay. So this is the TDC. You see here the inlet valve opens 10 degree before top dead center. Okay. And then what happens is after the air fuel mixer comes, then again the inlet valve closes. This inlet valve will close 10 degree after before 10 degree before bottom dead center. After the bottom dead center. This is the after one. This is the before one. Okay. You see when the piston moves from TDC to BDC, what happens is because of gasoline engine air fuel mixer comes in, and and again in the case of actual, this is in the case of the theoretical valve timing diagram. We normally tell the the fuel mixer and the fuel air mixer comes in the intake through the inlet valve at the TDC position, but it is not exactly happening at TDC position because in the case of actual, it will happen before and even the valve timing opens, closes, it will happen either in after or before condition. Okay, it is not going to happen theoretically. So theoretically, we have seen the piston moves from TDC to BDC where the inlet intake stroke comes, and then when the piston moves from BDC to TDC, you get the compression stroke. But it's not going to happen exactly at the TDC or BDC. Okay, so it is going to happen either before or after. We will see how it is going to happen. That is what this diagram is all about. I told you this TDC 10 degree before TDC, you are going to open the inlet valve opens, and again the exhaust in the inlet valve again is going to get closed so that it will arrest the incoming fluid. Okay, that is going to happen the 10 degree after BDC, which means when the piston moves from BDC to TDC. Okay, when the piston moves from BDC to TDC, what happens? Compression is going to happen. Okay, so the compression is going to happen. So this is second stage, so compression. Okay, and again the compression is going to end okay 5 degree after TDC. So you see here when the and again when the inlet valve opens, sorry, when the inlet valve closes, the exhaust valve is going to get sorry, when the inlet valve closes, you see here the compression is going to happen because you are going to lock both inlet valve and also the exhaust valve. Okay, so neither the exhaust system, exhaust valve will open or the inlet valve open. So here you're giving a chance for the compression to take place. So without any loss. Okay, so without any the pressure drop. You see here the compression is going to happen such a way that it moves from BDC to TDC by compressing the system of the air and the fuel in the case of the gasoline. Whereas in the case of diesel, you only the air gets compressed. Okay, and you see here then you also have the spark. Okay, the spark plug. Okay, the spark plug will happen. The ignition will happen 15 degree before top dead center. Okay, when the spark happens, what happens? You're going to get the compression in the power stroke. Okay, again the power stroke will happen when the piston moves from TDC to BDC. During this times, what happens is again the exhaust valve will also get closed. The exhaust valve goes 5 degree after TDC, and again you're going to get the power stroke. You see the power stroke, and again after the power stroke, when the piston moves from TDC to BDC, Again, the exhaust stroke is the last stroke where the exhaust valve opens, so that if the exhaust valve is not going to open, what happens is the exhaust gas will not go out. Okay, so you need to ensure that the exhaust valve is going to get open, and you see it opens 25 degree before top before bottom dead center. Okay, and again uh, again and again when it is completing, it is going to complete such a valve is going to get closed 5 degree after top dead center. So under cycle, the cycle gets repeated. So I will repeat once again. I will repeat this again. You see this, listen this carefully. The piston moves from TDC to PDC during the intake stroke or intake system during the intake stroke. This is the first stroke where the intake valve opens. And again, you see here the intake valve opens 10 degree before top dead center. And this is the first stroke. And again, after the first stroke, the inlet valve gets closed. Okay, and this will happen 10 degree after bottom dead center. And next stroke is nothing but the compression stroke, where it is compressing the fluid. Fluid is basically the air and the fluid, and then during the power stroke, and again during the power stroke, what happens? The piston moves from PDC to PDC, and again the exhaust valve opens 25 degree before bottom dead center. And finally, you need to close the exhaust valve, because again, when you close the exhaust valve, inlet valve will open. Okay, and the cycle continues. This is the example of a low speed engine of a gasoline. And when you come back to the high speed engine of a gasoline, let us see how it is working. Again, here the value will change between the engine configuration, and again it will also vary from the engine specification also. Okay, and you see here the case of high speed engine of a gasoline, the inlet valve opens 10 degree before top dead center, and again the inlet valve closes 50 degree after before the 50 degree after bottom dead center. And again once this gets closed, again you are going to get the compression stroke. Okay, we are going to compress the system, and then so before in the compression stroke only, you're going to ignite the spark. Because of that spark, you're also going to get the power, and the spark will happen 40 degree before top dead center, and you're going to get the power. Okay, power where the pressure shoots up. So the power stroke will end 55 degree before bottom dead center. When the power stroke ends, what happens? The exhaust stroke will start, which means the exhaust valve will open, and the exhaust valve will open 55 degree before bottom dead center, and the exhaust valve will open, and continuously exhaust gas will be expelled out. And again, the exhaust valve closes immediately 20 degree after top dead center. When this exhaust valve closes, what happens is again the cycle repeats by making sure that inlet valve opens 40 degree before top dead center, and the cycle repeats. Next, we will see the four-stroke diesel engine. Okay, here we are going to see only one configuration, not like low speed or high speed. See, so here there are some abbreviation out there. IVO stands for inlet valve opens. IVC stands for inlet valve closes. EVO stands for exhaust valve opens. EVC stands for exhaust valve closing, and FVW stands for basically the injection system, or fuel valve opens and the fuel valve closes. This is the basic abbreviation that we are going to use here in the case of a diesel engine. Okay, the inlet valve opens. Okay, 25 degree before top dead center. So when the inlet valve opens, what happens is basically the suction. Okay, this is suction, and then the inlet valve means the suction means the inlet valve closes 30 degree after bottom dead center. So once the intake stroke is over, then what happens is the compression stroke. Okay, in the case of diesel, only air comes in. Now you're going to compress the air. So the piston moves from VDC to DDC. And again, you see the compression stroke. The piston moves from BDC to DDC. And again, before it reaching the TDC top dead center, you are going to open the fuel injection. So here the fuel injection is going to start. The fuel valve open, which will happen 15 degree before top dead center. And what happens after that? The fuel injection is going to stop. Okay, or fuel valve is going to close. Okay, that will happen after 25 degree of the top dead center. Then what happens is the expansion is going to it's nothing but a power stroke. Okay, and the power stroke is going to over only if the exhaust valve opens, and you get a high pressure, peak temperature during the combustion, and it comes to the exhaust valve where you need to expel the exhaust gas, and this will happen. Exhaust valve will open at 45 degree before bottom dead center. Okay, and you need to go here, and this is exhaust stroke, and exhaust stroke is going to happen only if you complete exhaust valve closing. Basically, that will happen 15 degree after top dead center. And that is you see it is very important. That is one more term, very important term called valve overlapping. So valve overlapping is nothing but what? So this is the inlet valve opening. Okay, it will happen before top dead center, and you see this is the exhaust valve closing. Okay, and which is nothing but the end of exhaust valve closing. Okay, which is nothing but the end of exhaust valve closing. Once the exhaust valve closing over, then again what happens is the inlet valve opens. Okay, this process repeats. So how I can going to define this valve overlap? Okay, it is nothing but the time limit in terms of the time or in terms of degree. So here it's basically degree. The duration with respect to the in terms of degree of the inlet valve, the opening of the inlet valve against the exhaust valve getting closed, but again you need to ensure that the valve period is being kept open during the valve overlapping stage, and you need to have the value such a way it is too high. What happens is when it is too high, okay, there is a possibility you may end up with you need to understand the concept and you need to try it as per this. Okay, it's very important. Okay, and you also need to see the valve overlap. You need to mention all the criteria whatever that is mentioned. So in the case of the four-stroke petrol engine, the valve overlap is again it is based on the inlet valve opening and then the exhaust valve closing. What is the overall degree values? And you need to draw such a way what is there in the system, what is there in the presentation. You need to draw it in a very careful manner. And it is basically based on the four-stroke what I have explained in the first class. Okay, this is the overview. Okay. So when I say here the value again, it is not going to take place exactly. Okay, it is not going to exactly take place at 10 degree or it is not going to exactly take place at 25 degree. So it will vary depending upon the engine configuration. So just to give you an overview, the inlet valve opens in the case of a four-stroke diesel engine 10 to 15, 25 degree before top dead center. and the inlet valve is closing between 30 to 40 degree. Okay, it can happen either 30 degree or at 50 degree, and that is going to happen after BDC. And again, the fuel injection going to start. Uh, I told you this is happening during the compression stroke, and that is going to happen before the top cylinder. And during the power stroke, the fuel injection going to stop, and in between the injection starting and then the injection stopping, you are giving the time for the combustion pressure to shoot up, and then the pressure temperature goes higher. And basically, combustion is basically the injection and the fuel injection and the air gets mixed, and you get the combustion. And finally, you get the exhaust valve opening. It will happen 30 to 45 degree before the bottom dead center. And finally, you are going to close the exhaust valve for the last stroke to get complete. It will happen 15 to 30 degree. So this value, when I say it is 15 degree, the exhaust valve going to get closed. It's not going to happen at exactly 15 degree. So it will happen between 15 to 30 degree. Okay. But what you need when you're drawing the diagram, what is important is you need to look at the base value and then you need to draw. But when you're writing the conclusion, you need to write like this. Now we will see the two stroke. Okay, so inlet valve, exhaust valve you have in the case of a 4-stroke, whereas in the case of 2-stroke you don't have the valve. Okay, you have the port. One is inlet port and the one is exhaust port. You also have the transfer port. It is not mentioned here. Transfer port is the one which will transfer the air and the fuel mixture to the combustion chamber, which is aboard the piston in the case of a gasoline engine, whereas in the case of diesel engine, it will transfer the air to the combustion chamber aboard the piston, and then the air will mix with the injection fuel injection in the case of diesel, and basically there is one more port called transfer port. And that is exhaust port is there which will expel the exhaust system out, exhaust gas. So inlet valve is similar to the inlet port, and exhaust valve is similar to the exhaust port. Okay, but you also have the transfer port. Um, and again, what happens in the case of two-stroke? Okay, here in the case of two-stroke, you have only two-stroke where the intake stroke and the compression stroke will happen at the first stroke, and the compression expansion stroke or the power stroke and the exhaust stroke will happen at the second stroke. Whereas in the case of the fourth stroke, you have the suction stroke or the intake stroke, compression stroke separately, you have the expansion stroke or the power stroke separately, and the exhaust stroke. So here in the case of two stroke, what happens is the suction stroke and the compression stroke form a first stroke called here it is mentioned as a compression stroke, and the second stage is nothing but expansion stroke. So here you have for every one revolution of the crankshaft you're going to get the power, whereas in the case of 4-stroke engine, for every 2 revolution of the crankshaft you're going to get the power. Okay, you see here now the same procedure is also applied in the case of 2-stroke engine. Again, 2-stroke is also related to petrol and also gas and also the diesel. Always remember that in the case of a gasoline engine, you have air and the fuel mixture which is coming into the inlet during the intake stroke, whereas in the case of diesel, only the medium is air. Okay. Okay. First, we will see the system. Like the ignition starts or ignition occurs 20 degree before TDC. Okay. When the ignition happens, okay, which means here basically the air fuel mixture. So air is also going to happen, and also here when ignition starts, what happens? The air ignites with reacts with the fuel. Okay, so you also get the combustion, but the combusted gas is going to get into the inlet, basically the top dead center, which comes before TDC, 20 degree before TDC. It's nothing but the first stroke where you're going to compress also. And again, you see, doing this stroke, what happens? The inlet valve opens, and again, you see the inlet valve opens when you see, you're going to ignite the fuel, which means you are giving the chance for the ignition to take place. Okay, and you see here the inlet port open. It means you are allowing the exhaust. You are allowing the inlet system, basically the air mixer, air and fuel mixer, and it will happen 35 degree before bottom dead center. And once this opens, what happens? You're going to get a compression stroke. I told you the compression stroke is the first level of stroke. And once the compression is going to take place, what happens is you are going to have the expansion. Okay, where again at the end of the expansion stroke, the exhaust port. Okay, the exhaust port will get open. Okay, the exhaust port will open basically 43 degree before bottom dead center. And you also have a system of such a way. You see here the inlet or opening, inlet or closing, inlet port. So here is basically the port. Inlet port opens and inlet port closes. So inlet port opens. You see the inlet port opens 35 degree before bottom dead center, and again it closes 35 degree after bottom dead center. And so this is where the first level of stroke is going to get over. And when you look at exhaust port, which is opening and closing, you see the exhaust port opens during the expansion stroke, which will happen 43 degree before bottom dead center, and exhaust valve closes. So that when the exhaust valve closes, what happens is again you're going to make sure that you have some period where the inlet port will get open. So the exhaust port will open again 43 degree after bottom dead center. And again, when I say degree, it is not going to be exactly at that particular degree. You have some variation. Okay, this variation is very much important. When I say 40 degree or 35 degree, it's not going to happen exactly at 35 degree or 40 degree, but you have again the different. You have some the gap according to the engine configuration. This will get varied. You see here. You see, this is very much important. So during the compression stroke, which is starting the first stroke, where you have the exhaust port closing condition, and then the second stroke is nothing but the one where the exhaust port is going to get open, so that the exhaust gas goes out to the system, and you have the charging where you get the combustion when the transfer port opening and the transfer port closing. Okay, basically you have I told you we have a transfer port. Okay, when the transfer port opens, okay, what happens is this will help the air and fuel mixer or the air mixer to reach the combustion chamber. It is about a piston. When it is closing, okay, when it is closing, the exhaust port will open. Okay, so during the charging, during the combustion, the transfer port which is helping the two-stroke engine. Okay, we will see the two-stroke diesel engine now. We have completed the gas engine. Now we'll see how the two-stroke of a diesel engine comes into picture. So I have given the overall details in explanation. Also, we will look into it in a more detailed manner. So this is the port diagram of a two-stroke diesel engine. The first again you get the first compression stroke. Next stroke is nothing but the expansion stroke. And scavenging, but I told you we are going to expel exhaust system, removal of the burnt gas to the exhaust. And during the time, what happens is you're also having the transfer port opening and transfer port closing. So transfer port opening will happen during the charging system, which is nothing but the combustion process. And once the exhaust port opens, the transfer port gets closed. The same process is repeating here. So here in the case of the diesel engine, you have the fuel valve opening and fuel valve closing. Whereas in the case of the petrol engine, you have the ignition. You see the fuel valve opens 15 degree before TDC, and rear valve closes 20 degree after TDC. So basically it's nothing but the fuel supply. So once the fuel supply is over, what happens? You're going to get the expansion, okay, where you get high things and again you get the exhaust. Okay. But first is nothing but basically the compression stroke, where your inlet port opens, um, and then the inlet port closes. This is same cycle basically. So you have the detailed explanation. Okay. And again, this degree it will vary, but what you need to, when you're drawing the diagram, you need to ensure that following the stages and accordingly you need to draw it. Can be drawn in a freehand sketch also. So the next important topic is the engine valve overlap. We have seen the engine valve overlap in the ball dynamic diagram. So what is the overlap? Okay, overlap is the one. Engine overlap is nothing but the inlet. I told you it is between the inlet valve opening and then the exhaust valve closing basically. Okay, but you listen this very carefully. So inlet valve opening and exhaust valve open, which means the exhaust valve is kept open till it is going to get closed. Okay, till it is going to get closed. Okay, so when the moment the exhaust valve closes, the inlet valve opens again. The moment the exhaust valve closes, the opening of the exhaust valve are going to end. So here it is nothing but the period between the inlet valve opening and the exhaust valve, which are kept in open stage. I told you the exhaust valve will open during the exhaust stroke. Okay, up to what moment it is going to get open? Okay, that period you are going to have it as a overlap period. And you see here, this inlet valve opening and exhaust valve will happen at the same time. And doing so, this will happen at the end of the exhaust stroke. And again, this will also happen at the beginning of the intake stroke. So if your intake valve opens before top dead center and your exhaust valve closes after TDC, you may have the overlap. But it is not that you need to you should define such a way the period of valve opening condition between intake to the top exhaust, that is called as overlap. But looking at the diagram, you may feel that it is nothing but the period between the intake valve opening before TDC we have seen and to the top the exhaust valve closing after TDC. But correctly speaking, it is nothing but the period of time where inlet valve opening and the exhaust valve opening are going to happen at the same time. That is the correct meaning. But we cannot have the diagrammatic representation. So what we are going for a diagrammatic representation is between the inlet valve opening and then the exhaust valve closing is starting the valve overlapping. But you have to ensure that before this exhaust valve closing, the exhaust valve is kept open. Okay, which means the time duration between the inlet valve opening and the exhaust valve opening at the same time they call this as valve overlapping. So we will see that with the help of a graph. See the piston moves from TDC to BDC, BDC to TDC. You have a 2-stroke or 4-stroke. Okay, irrespective of the stroke engine, what happens is you see here this will happen over 720 degree of the crankshaft location, and you have the wall lift. So valve overlap will happen only in the case of 4-stroke, whereas you don't have a system called port overlap in the case of the 2-stroke engine. This overlap is basically, even though this overlap is also applicable for a 2-stroke engine, but normally we don't have the valves there, and again we are going to concentrate more towards the 4-stroke engine respect to the valve overlap. And you see here, this is nothing but a valve overlap period where the inlet valve and then the exhaust valve are kept open at the same time. So higher the degree and the lower the degree will also influence the power and then the torque of the engine. So it should be kept in such a way the optimum level of degree should be maintained between the exhaust stroke and then the exhaust valve opening and then the intake valve opening. So this is the location where it will contribute or it will determine what is the valve overlap period for your engine. In other words, the valve overlap is nothing but both inlet valve and exhaust valve are open for a short time. Okay, it's not that exhaust valve closing or inlet valve opening. So it is nothing but both inlet valve opening and exhaust valve opening at the same time. Uh, this period called is a valve overlap period. Okay. So just we have covered the scavenging and then to force we have seen the wall timing diagram of two stroke CAS engine and wall overlap we seen. We also seen the scavenging and just all these processes are already there. Okay, I also explained you the volumetric efficiency and again it's the basics again. You can look all these details in a book called John B. Haywood in a chapter number 6. Uh, Now I will also give you the overview of just a graph alone. Then I will go with the the fuel flow in a combustion. You will see the gas exchange process basically. Um, all these details are given in a John behavior. So you have seen what is called the volume efficiency. It's basically the mass flow rate of the air. Uh, but you have different the values. You have different. And look for more details into that book. See, basically, the volumetric efficiency of the engine is basically affected by various parameters and also based on the engine design and also based on the operating variables of the engine. The volumetric efficiency of the engine is also depending upon the compression ratio of the engine speed, RPM, and how you are going to design the inlet and the exhaust manifold and the port design. Basically, you need to design such a way there's a smooth flow of air intake system so that you can increase the volumetric efficiency. And you see, basically the lift, wall lift, basically the geometry is very much important. Okay, so the wall overlap should not be higher. Also, there is I think some question here come will wall overlap will affect the engine performance. Yes, it will affect, but you need to ensure that it is not going to the higher level. Okay, because obviously the wall overlap will be there. You can't avoid it. Okay, and because you need to have some time where you need to give some the time period between the valve opening and closing. So you can't avoid that obviously, but you should ensure that it's not going to highest or going to the higher side. When it is going to go to the higher side, then it will affect the performance. Basically, the power and torque issue you might undergo. So that is what the answer for that. And there might be the other reasons how we can look for increasing the volumetric efficiency. And this volumetric efficiency is also based on the fuel type, what you're going to use, what is the air fuel ratio, because you have lean mixture, rich mixture, and against stoichiometric mixture. So according to this, your volumetric efficiency also will go higher or lower. But again, you need to ensure that you are going to have higher volumetric efficiency. When you have higher volumetric efficiency, obviously your compression efficiency will be higher, which means your mechanical efficiency will also be higher. There's a reason where it's also based on a fuel type. I told you you have two type of fuel. One is gasoline and diesel. So the volumetric efficiency of diesel is going to be higher than that of gasoline because here only air comes in the case of diesel, whereas air fuel mixture comes in the case of a gasoline, and it also depends on the fuel type. Okay, and this volumetric efficiency is going to be higher, then this will also have the influence on the mechanical efficiency and also the combustion efficiency of your engine. So this is the volumetric efficiency of the ideal cycle. So all these details are given in the chapter 6. You can have it for your reference. It is more of derivations, but you need to understand the formula. The basic formula is nothing but the mass flow rate of the air to the top, the displacement volume. Here, rho is nothing but the density of the air. Okay. So equivalence ratio is nothing but the air fuel ratio and to that of pressure ratio. So that here it is nothing but the ratio of air inlet pressure to that of the mixture of the inlet pressure versus the equivalence ratio, basically the fuel air ratio. This will also vary with respect to different composition of your fuel. Okay, so your fuel, okay, it can be a gasoline or a diesel is having different composition of carbon, hydrogen, and oxygen. So depending upon the different configuration of your fuel, your pressure ratio will vary according to the fuel air ratio, and this will also have the influence on the volumetric efficiency of your engine, and also the flow of gases into the engine. See now there is a graph which indicates the x-axis as the pressure ratio. Here the pressure ratio again is based on exhaust pressure to the top the inlet pressure. P stands for exhaust pressure, PA stands for inlet pressure, which is nothing but the pressure ratio, and this is nothing but the volumetric efficiency of the engine. Okay, so higher the pressure ratio, and you also have your volumetric efficiency is also going to get decreased. Okay, and you're going to see what is your compression ratio also. Okay, you're going to have the mapping between the compression ratio and then the volumetric efficiency considering the pressure ratio. So you can also determine what should be the compression ratio for your engine. Okay, so this graph will also help you to find out the selection of the compression ratio. So higher the compression ratio, what will happen is you have the knocking effect in the case of a gasoline engine. So it's always important to have the right amount of selection of the compression ratio for your engine. So this graph will help to consider the system having the proper amount of compression ratio. See, this is the graph showing the speed versus the delta P pressure drop. So here, this is considering all the friction loss. I told you have different type of friction. Basically, when the engine is running at higher RPM. Okay, so this friction loss will have the friction power that will also influence the brake power and then the indicator power of your engine. Indicator power is the one you are going to get the power from the cylinder, say the cylinder, and brake power is the one you're going to get from the. You are going to measure it from the crankshaft, outlet of the crankshaft. This nothing but this graph indicates the pressure loss in the system of a 4-stroke SA engine. They are determined under the steady flow condition. The flow is considered to be steady. Okay, and here they assume that the stroke is 89 and bore is 84. This is just a graph. The detailed explanation are given in that John B. Haywood. You can look into it. See, this volumetric efficiency is based on the manifold pressure, inlet manifold pressure. So the air flow basically, and again the exhaust manifold also, because you get the exhaust pressure from the exhaust manifold. So the ratio between the exhaust pressure to the inlet pressure, you call that as a pressure ratio. So I told you, based on the pressure ratio, you're also going to have the volumetric efficiency. Based on that, you're also going to have the compression ratio selection. And again, you see, based on this, the pressure variation, you see here, you need to see how your engine performance is going to happen considering the engine bore or engine torque. You see here the graph showing the inlet pressure versus the exhaust manifold pressure. So you see different RPM or different speed, and again different torque is also given. Here only they mentioned the speed in RPM 1200, 1600. When we also look at when the speed increases, what happens is when the speed increases, the exhaust manifold pressure gets increased. Okay, so higher the speed, the pressure is going to be higher on the exhaust side. So when there is higher in the exhaust manifold pressure, what happens is the pressure ratio is going to be higher. when there is pressure ratio higher, what happens is your volumetric efficiency is going to be higher. So higher the volumetric efficiency, what happens? Obviously, your combustion ratio is also going to be higher. When that is the reason you also have the compression ratio higher in the case of diesel engine, where it will go beyond 15 or 20, but it is not. It is lesser in the case of a gasoline engine. So it is having the indirect comparison. You can also correlate between the pressure ratio, the volumetric efficiency, and the compression ratio. You can look into the details more about this in the case of the John B. Haywood book. I'm just rushing it. Okay, you see again there is the variation with respect to the engine speed or the engine speed with respect to the mean piston speed of the engine, and then the efficiency. Okay? Basically the volumetric efficiency. So you see here the diesel is considered to be the high volumetric efficiency considering the different main piston speed of the engine compared to that of the spark ignition. See again this volumetric efficiency will also have uh, parameters which will determine uh, the volumetric efficiency of the engine. If you have the backflow or if you have the restriction to the air, your volumetric efficiency will reduce. Okay, and you need to do some fine tuning by doing some design so that your volumetric efficiency can go higher. And you have some the pressure effect. So you need to arrest. You need to do some fine tuning to into the RAM effect we call. And if you do this, your volumetric efficiency is also going to be higher. What is called a RAM effect? We see that. Okay? So it is basically the pressure. So you have the inlet pressure, basically the air which is coming to the inlet manifold. Okay, and again it will vary with respect to the different cylinders. It's not going to be uniform. Okay, so suppose we have 3-cylinder, or if we have 4-cylinder, or if we have 2-cylinder, the variation of the pressure will happen according to the different the configuration. So what is perspective of the variation in the pressure of the cylinder? Again, again the flow is sometimes it's not going to be steady. Okay, and according to that, what happens will also have the influence on the volumetric efficiency, and this will also have the inertia because of the higher RPM. It also develop the inertia into the system. Um, so, what is the advantage of this effect called a RAM effect? Is that uh, it's not it's not that it is going to have a high influence on the volumetric efficiency. It will have, but you see, I told you, you have the inlet valve opening and inlet valve closing respect to the water timing diagram you've seen. So you see the last important time, the inlet valve is going to get closed somewhere 40 to 60 degree after bottom dead center. Uh, is you take the part advantage to go for the RAM phenomena, the RAM effect, where you are also going to determine the amount of the variation with respect to the other parameters, considering the inertia, speed, pressure, uh, and uh, and also the overall system configuration with respect to the combustion parameter also. And again, here RAM effect is not only to the combustion, but also here, as we deal with volumetric efficiency, basically we are going to deal only with respect to the inlet system. Okay, inlet system is basically the intake manifold. How much, how the air is going to get flow into the system very smoothly without any restriction, with proper velocity, with proper. And you also have the throttle valve. Okay, you have the throttle valve which will open the quantity of required amount of air into the intake system. So this will help. So you need to ensure that you're also having the proper fine tuning of the RAM effect so that your volumetric efficiency is going to be according to the directions is there in the specification. So these are the different graph that you can see it. Basically, it's all self-explanatory. Okay. So we see the flow, how the flow is going to go through the valves. We have inlet valve and exhaust valve. This is the configuration of the valve. This is the valve diameter. Okay. And this is the valve seat. Basically, this is a valve seat width. This is the seat angle, and even the system configuration is very important. And this is system diameter. What you have the inner seat diameter called D. Open valve geometry, and you see these are different types, different methods how you design the valves. You have different specification. Okay, you need to have, sometimes you need to have the largest possible radius so that the amount of air which is coming in can be made with more area, and you need to have some the protrusion. Okay, the protrusion should be lesser. You see, it's not protrude too high. Okay, it should be uniform. It is the valve when it is lifting. Okay, we have low lift and also high lift. These things you can look into it in a more detailed manner. I also explained about the scavenging. Okay, you have the scavenging. You have the loop scavenging. You see how it forms the loops, and you also have the uniform scavenging system. Each system is having different advantages, disadvantages. These details also given in the book. You can look into it. Again, you see, this is very much all the formulas very much important, and see on what basis the modeling of the scavenging parameters are being done based on the air flow rate and also the mass flow rate, and you have the charging efficiency percentage, considering that the delivery ratio and the efficiency of charge scavenging also how it will vary. You can look into all these things. So we have seen the valve flow, how the flow of system comes to the valves, and similarly they also given the flow through ports. You have again the port is of, I mean, it is of circular shape, square shape, uh, and how you are going to design the port is also very much important. So we have seen the low speed and high speed engine for a four-stroke petrol engine. So here, in the case of high speed engine, the combustion stroke is less. Uh, yeah, so you're comparing this with the compression. So here, um, the exhaust, sorry, the inlet valve is going to close only after 50 degree after the bottom dead center, whereas here it's going to close 10 degree after the bottom dead center. Yes, the stroke is going to be, yes, again, when the speed is higher, what happens is you cannot control the air fuel mixture. Okay, the compression can easily compress it. Okay? And again, that is easy, but it is very difficult when you assume that you have the nose, which is acting as an inlet for your human body. When the amount of air is coming very highly, okay, what happens is you breathe more, okay, and again it is very difficult for you uh, to close it immediately. Okay? Because even if you try to close, because the air is coming frequently, it's very fastly. That's the reason when you're going for high speed engine, the amount of air which is entering into the system. So in the case of petrol, it's basically air plus fuel, and in the case of diesel, again, it's basically the air. And again, even this valve configuration will also vary with respect to the different speed of the engine. I have categorized only with respect to the petrol engine, low speed, high speed, even for a diesel application. When the engine is, the vehicle is running shipping condition, the vehicle is running in highway condition, this configuration will vary. Yes, of course, when the speed is going to be higher, the compression stroke is going to happen at anyway. So we will see another important topic called the fluid motion in the combustion chamber. The various topic basically. Okay. So your see, this is nothing but the turbulence level of your gas which is flowing inside your engine respect to the engine speed. You see here when the engine speed, engine RPM is going to be higher, the intensity of the turbulence going to be higher. Okay, and you see important thing. Okay, this is very much important. Here the spill motion going to is the first diagram which explains the spill motion within the engine cylinder. Okay, and you have different methods to generate a spill motion. See, I told you the combustion chamber is nothing but the place where air and fuel gets mixed, and you're going to get the combustion out of it, and that will happen about the piston. Okay, that will happen about the piston. So you can create the turbulence when the turbulence, or you can also create the spill. That is a spill motion. Okay, spill. Okay, spill motion, and again you can see how this is the airflow. Okay, and again you have different valves and or configuration. You have port configuration because of two-stroke engine. Okay, and the air entry, how the air is entering to the cylinder, maybe it can be either in a tangential direction. You see, the air is entering in the tangential direction, and it is reaching the combustion chamber. And again, you see, this is the airflow. Uh, okay, which is entering into the intake manifold or the intake runner. So again, this is intake manifold. Okay, and you see this is also entering into the valve, uh, basically the control valve. Okay, how the air is going to enter. So based on this, you are going to get a swivel motion for your configuration. Okay, so that's the reason. How the fluid. Okay, fluid is nothing but air, and in the case of the combustion chamber where air and fuel gets mixed, how the flow is going to be with respect to the turbulence, with respect to the spill, and how that will have the influence on other systems. So the another important thing is nothing but the spill ratio. Spill ratio is basically a dimensional parameter which is used to identify, quantify the rotational motion within the cylinder. And this field ratio is also defined in two different ways with respect to the angular speed, engine speed, and again the field tangential speed, average distance speed, etc. Uh, so I'm going to take the field ratio in y-axis and the crank angle in x-axis. See, you also know that you're going to have the intake, compression, power stroke. Basically, the combustion is going to happen, and then the expansion. So here. Is how the speed ratio is going to perform at the different stroke of your engine. Intake stroke, compression, combustion, and the expansion. Uh, and again, this speed ratio is also a function of a crank angle. This is an example of a SA engine. And again, the speed is going to be high in the intake process. Okay? Because what happens? The air entering. Okay? It causes more spill. Okay? And again, the spill ratio is going to be higher during the intake stroke. And again, then it is going to get reduced because of the drag you are going to have during the compression stroke. Okay, and again there is again this spill ratio is going to be higher because the pressure shoots up. Okay, I told you this fill ratio is also based on the function of the engine speed, and again it also depends on the average piston speed and the angular speed of the engine. Okay, so in the case of the combustion, what happens is once the combustion starts, the pressure shoots up. When the pressure shoots up, again it's also a function of the speed ratio. Again, your speed ratio is going to be higher, uh, and uh, and again you're going to get expansion, because again expansion you're also going to have the drag similar to the drag what you get here. That's the reason you get lesser speed ratio here. And it's always important to have the high amount of swill so that you get better performance. Uh, so even you need to look for the design of your system. Basically, the combustion chamber system, you need to have high swill ratio, so that you need to have high swill ratio so that the air and the fuel mixture and the air mixture coming to the striking with the fuel, so you get the better performance basically. This is the combustion chamber. You always remember that combustion chamber is the place where the combustion is going to take place. So here you need to design. This is all about, you're going to design the combustion chamber with different types and different configuration, uh, by ensuring that you are going to have different varieties like swill or turbulence or the squish or any irrespective of any forms. So you are ensuring that you are going to have providing the more volume, okay, and again you are providing the place where complete mixture is going to take place. Mixture in the sense air and fuel mixture. This is the two different geometry that you have for a combustion chamber. The first geometry is the one having the clearance volume in the head. Okay, the clearance volume having in the cylinder head, and this is the one. This is the configuration where the bowl in the piston. This is the piston bowl. Okay, this is the bowl. This is the piston bowl, and again this is the crown, which is nothing but the top portion of the piston, and you have a combination of the piston bowl and again the crown configuration, in the case of B configuration basically. So here the combustion chamber geometry basically deals with having the more amount of or more clearance volume near the center of the cylinder, and higher the volume will also increase uh, your squeeze and tumble, and it will also decrease the flame travel distance on most of the combustion process, which means your flame travel distance should be lesser. When the flame travel distance is lesser, what happens is uh, lesser the flame travel distance, you can easily combust the fuel. Okay, so when the flame is traveling very large direction or large distance, okay, there is a possibility that there may be some unburned gas left out. Unburned fuel may be left out, which will lead to carbon monoxide hydrocarbon emission. Okay, so the main objective is to burn all the fuel inside the combustion chamber by ensuring by squeezing or tumbling it, or by swirling it, or by creating turbulence. You need to ensure that you are going to decrease the flame travel. Flame is nothing but that will happen after the combustion. It means the air and fuel gets mixed, you get a combustion, which means the flame gets traveled. And again, you should not allow the flame to travel to a long distance. Okay, you should reduce the distance also. And this is the squish and tumble action, uh, where this is the combustion chamber. This is the piston crown, okay, and about the piston, okay, about the piston, and inside near to the piston crown, which is the top portion of the piston, you are going to create uh, the action, which is nothing but the squish action. Um, so here, you look at this squish action. What happens is uh, this you're going to get the, the combustion radially inward, and the radially inward motion of the gas mixture. Okay, it comes in a radial direction, and And with this radial inward direction the motion of the gas mixture, you call this as a squeeze. And it also add to another mass between the cylinder to mix air and fuel. And this maximum squeeze velocity will happen before top dead center. Okay? So again, when the piston moves from top dead center to BDC, you get the different pattern. So, but basically, the data says that the maximum squeeze velocity occurs at about 10 degree before top dead center. When the piston moves BDC to BDC, and before reaching the TDC position 10 degree, you get the maximum squeeze. And you also have one more term called reverse squeeze, okay, which will help to spread the flame during the later stage of combustion. I told you the flame front or the flame distance should be lesser, but you get a better performance. So you need to avoid the reverse squeeze. Squeeze is always good, but when the squeeze is going the reverse direction, squeeze is always good where you're allowing the radial movement of the exhaust, the gas for the combustion to take place. But when there is a reverse squeeze, then it will spread the flame, and again the flame will travel to the long distance. Okay, so that again it will also create some issues. So it's always good to arrest the reverse squeeze, whereas you need to encourage or you need to design such a way you need to provide a squeeze for it. And you also have a tumble tumble action, which is nothing but it's a rotational motion about the circumferential axis near the edge of the clearance volume. Okay, here the rotational motion is going to happen about the circumferential axis near the edge of the clearance volume. Basically, here you want the piston crown and the piston bow, okay, in the cylinder head. Okay. So whatever it is, irrespective of the system configuration, either you're going to create a turbulence or a spill or a squeeze or a tumble, it's happening inside the combustion chamber, which is above the piston. Okay, and it's all dealing about the pattern. You have the other two very important type called the divided combustion chamber and the crevice flow, and you have these two important types of the combustion chamber. One is the divided combustion chamber. So here what happens, I told you you have two type of mixture, one is lean mixture and one is rich mixture. Lean mixture is the one where you have high air and less fuel, and the rich mixture is the one where you have more air, more fuel and less air. In the case of divided chamber, what happens is this basically we're dealing with the case of AC engine. You have the secondary chamber, and then the where the secondary chamber you're going to have the rich mixture where almost contains about 20% of clearance volume. So this is going to happen at the clearance volume VC position, okay, which is about the combustion chamber. And in the case of the main chamber, we are going to have the lean mixture, which is above the piston, which is directly above the piston. Okay, it is directly above the piston. Okay, so you are going to divide the combustion into two regions. One having rich mixture, and the one is having the lean mixture. Okay, according to this, you can divide it. And what is the advantage of this? Okay, this primary chamber or the secondary chamber, this will also help to expand the flame, and the expands it will help to expand, but at the same time it will also ensure that it is not going to travel to the higher distance. Okay, and this will help for a good ignition and lean charge. In the case of a primary chamber for a good fuel economy, this helps for a better mileage also. And this I told you there is a different type of losses are happening in an engine: blow by loss, blow down loss, pumping loss, time loss, heat loss. There are different type of losses which is happening inside the engine. And one important loss is the blow by loss, where the exhaust gas leak the past piston and ring. That is nothing but a blow by loss. So you need to reduce the blow by loss. So when you reduce the blow by loss, your engine efficiency also going to be higher. So to reduce the blow by loss, you need to have the combustion chamber. You need to design the combustion chamber such a way it is having the crevasse flow, which is basically a flow which will ensure that you are not going to have the flow by for your system. This is the leakage will happen through the piston ring, and that goes to the crankcase. Leakage is nothing but the blow by gas basically. And this is the valve, previous valve, basically the cylinder valve basically. When you have the previous flow or previous valve, basically uh, that will help to arrest the blow by gas. And because when you have the high blow by, then what happens is this will also affect your piston. When it is affecting the piston, piston is basically the power producing part. Right? This will affect your power. And sometimes higher the blow by will also sometimes is your piston. Okay, so it's always important to design the combustion chamber considering the less blow by providing the proper crevices to the wall so that the flow will be uniform and you can arrest the blow by. All this explanation is again given in chapter number 6 in a book called Villiers W. Book. You can look into it. We have various designs used on the end of piston ring to reduce the blow by using the different devices. You can have the different systems, the different uh, configurations. Okay, you look at this. During the combustion stroke, what happens is the pressure shoots up. Okay, the pressure goes to high pressure, which is the peak cylinder pressure we call. Uh, so you have three different stages. One is the pressure having the high peak cylinder pressure, and next one is the pressure between the compression ring, and third one is nothing but the crankcase pressure. Uh, so when combined to the cylinder pressure, the pressure between the compression ring. So you have three type of ring in the case of the piston, top ring, compression ring, and then the oil ring. So when the pressure between the compression ring, you have the top ring and the compression ring. The pressure between the compression rings going to have the pressure which is lesser than the peak cylinder pressure of your engine. And again, you have the last one is the crankcase pressure, where exhaust gas which is leaking the piston ring go to the crankcase pressure. Uh, so you see the pressure is going to be lesser than the P1 and P2. So what happens is, if suppose if in case any blowback occurs, okay, the blowback gas goes to the crankcase and it will also increase the crankcase pressure. Yeah, when the crankcase pressure goes, again what happens is it gives additional load to your cylinder block. Okay, basically your combustion chamber, it gives additional load. Uh, when it is doing additional load, it will also increase your pressure, which means it will also uh, create some additional pressure build-up basically, and it will create some problem basically. Because unnecessarily we're creating an additional load, thermal load, the form of the because the blow by is nothing but exhaust the gas. It is also having the temperature, it is having the load, it is having the pressure. So this will also affect your overall system configuration also. So that's why you need to have the proper amount of design of the combustion chamber so that you're not going to get a high amount of blow by gas. Uh, so you can explain, you can see all this into the, okay, this is a chapter called the fluid motion in a combustion chamber, within the combustion chamber. This is coming under the chapter number 6 in a book called Villiers W. Whatever I have given, it is more given in depth and look into it. Yeah, we have seen the swirling, we have seen the turbulence, and the more details are given here. You can look into it. Okay. So there are some questions which are coming with respect to the squish and tumble system. I'll explain that. Um, okay. Uh, the tumble action is caused by the squish is happening when the piston approaches when the piston is approaching the top dead center. The piston moves from TDC to BDC during the intake stroke, and from BDC to TDC during the compression stroke. Okay, when the piston is moving from BDC to BDC, okay, what happens? The compression takes place, and again during the compression, you also going to get the fuel injection. Okay, before top dead center. So basically, the tumble action is been caused by the squeeze. Again, I told you squeeze is nothing but the tangential flow of the air. Okay, and again, now I'm telling you about with respect to diesel engine. Okay. With respect to the gasoline, again, the term will vary. In the case of gasoline, both air and fuel. But now I'm discussing with respect to gas diesel. Then I will explain about gasoline. So when I talk about the diesel engine, what happens is the tangential flow of air which is coming to the chamber, which is above the piston bowl. And again, when the piston moves from BDC to DDC, okay, what happens is the squish is different, tumble is different. Squish is basically the radial amount of the radial movement, the air coming to the combustion chamber, whereas this tumble is basically the action which is going to get out of the space when the piston moves from BDC to the TDC. And what is called a tumble? Okay, it is basically the tangential motion of the air. When the tangential motion of the air, when the piston moves from BDC to TDC, they're going to have a tumble, which is nothing but a rotational motion. This will rotate, okay, about the circumferential axis. So this is basically a circumference, okay. It's basically it is having the layer or a zone where you gonna get the circumferential area for a particular combustion chamber, okay. And this is basically the rotational motion because you get the rotation of the system about the circumferential axis, which is near to the edge of the clearance volume is inside the piston bowl or in the cylinder head. Okay, so how I can differentiate the squeeze along with a tumble? Okay, squeeze is basically the air which is coming to the tangential direction in the case of diesel. Now, when I speak with a petrol, both air and fuel mixture comes. Okay, and this squeeze is basically a tangential movement again. And again, when the piston moves from BDC to 2DC, what happens is it compresses the one, and again you get the case of diesel you get the injection, and in the case of gasoline you get the ignition. But you see here, when it is going to compress, irrespective of diesel engine or a gasoline engine, you, the, the air, the mixture is going to have it is going to behave in a rotational movement. Okay, it is going to have the rotational movement, uh, which is above the piston volume or the piston bowl, or it is near to the edge of it is near to the edge of the clearance volume. Uh, and what is important is you need to ensure that you are not going to have more amount of reverse backflow for this. Okay, when you have the reverse squeeze, what it will affect the performance. And again, when you have the reverse during the compression, okay, when the piston is moving from BDC to DDC, you will not have a sufficient amount of air fuel mixture or air mixture to compress. Okay, instead, the reverse squeeze, what happens is instead of the tangential movement of the air coming to the combustion chamber, the reverse squeeze will cause a back pressure, okay, and it will restrict the amount of air coming to the freely into the combustion chamber. So it causes a reverse effect, uh, and that's the reason we need to avoid the reverse squeeze, and we need to go for it. So the details of the divided chambers, everything is given here. But I told you that you need to avoid the piston bubble flow by gas by providing the upper the crevices. The pattern is given. You can have the different pattern. I have explained you the pressure versus crank angle. See, you can also do the simulation using your system, basically the mathematical model. So you need to give some inputs for this. So we will see what are all those inputs. You need to consider the engine bore, stroke, piston pin offset, cutting rod length, compression ratio, valve diameters, angles, TDC values. You need to give all this as input. Okay? Um, and correspondingly, you get the output in the case of the formula. You see, we have seen the pressure versus volume. Okay, assuming when the pressure is going to be higher, pressure is going to be lesser. It is an example of a general motor simulation. So what is the output you are going to get? Okay, this pressure versus volume will give you the indication of the air movement for your engine, and according to the air movement, and then you are going to get the combustion. And once you get the combustion, you are also going to get the nitrogen oxide emission, carbon monoxide emission, hydrocarbon emission. So how you are going to get the output? Okay, considering all the inputs. Uh, and again, you need to consider the adiabatic condition. There is no heat loss you need to consider during the simulation. So all these details are given there. You can look into the chapter number 6 of uh, William W. Blue book. And there is one more book called John B. Haywood. I will explain that.